So, in this lecture we will continue with our discussion on properties of Markov processes and how they can be used to analyze probabilistic characteristics of response of randomly driven dynamical systems. A quick recall of what we did in the previous lecture, we showed that for a Markov random process the nth order joint probability density function can be expressed in terms of the initial probability density function and products of what are known as transitional probability density functions. So, a complete specification of a Markov process therefore would be in terms of the initial probability distribution function and this transitional probability density functions for different choices of T1, T2, T3, Tn and for different choice of n. We also showed that the transitional probability density function need to satisfy a compatibility condition known as Chapman-Kolmogorov-Smolchowski equation, where if we consider 3 time instants x1, x2 and tau, so that T1, T2 and tau, so that tau lies between T1 and T2, if we consider the transition from T1 to T2 and look at transition from T1 to tau and tau to T2, we should get the same answer. So, for that to happen the transition PDF should satisfy this condition and this is known as the Chapman-Kolmogorov-Smolchowski equation. We also went through a somewhat tedious derivation of the governing equation for evolution of probability density function of a scalar random process. We showed that this equation known as kinetic equation has the form dou p by dou t plus dou lambda by dou x equal to 0 and we discussed the associated boundary condition and the initial condition. This lambda of x comma t is expressed in terms of the probability density function and quantities denoted by alpha n, which are known as derivative moments. So, if we have to utilize this kinetic equation to solve any given problem, we should first evolve a method to determine these derivative moments, because they are the parameters in this governing differential equation. So, in this lecture we will consider some of these questions and we will begin by considering some properties of simple random walk and how they behave as delta x and delta t goes to 0. This I had discussed in one of the earlier lectures. We will proceed beyond what we did in the previous lecture. So, let us consider xi I1 running from 1 to infinity to be a sequence of identically distributed and independent random variables with 3 states. Probability of x equal to delta x is p, probability of x equal to minus delta x is q, so that p plus q is 1. So, the expected value of x would be delta x into p minus q and mean square value would be delta x square into p plus q. P plus q is 1, but I still choose to retain this as p plus q. Variance would be the mean square value minus square of the mean and we write this in terms of the mean square value and the square of the mean and manipulate these expressions and we get the variance to be 4 pq delta x square. Now, let us consider t to be the time axis and let us divide the interval 0 to t into n sub intervals, each of width delta t, such that n delta t is t. Now, I define S of t as sum of xi from I equal to 1 to n. Expected value of S of t is the expectation of the right hand side, which I show this to be n into p minus q into delta x. Now, substituting for n in terms of t, I can write it as t into p minus q delta x by delta t. Variance of S of t is 4 pq delta x square into t and that I can write it as 4 pq t into delta x square by delta t. Now, this is a simple random walk. So, what we are doing is we are considering n time instants, and at every time instant I am tossing a coin, and if I get head I will move this way, and if I get, I mean actually one dimensional, I will move backward or forward depending on whether I get tail or head, and S of t tells me after n such tosses where I am in this time axis. Okay. So, we are executing random walk on a line, and that we show, for example, forward movements if I show on this direction and negative 1 in this side. Suppose at this moment I get a head, I move up, I stay put till the next toss, and if I get head I move up, stay put, move up, stay put, come down, so on and so forth. So, this is one realization of a sequence of toss. Okay. So, at any time t, S of t will tell me my position on this line. So, S of t is known as a simple random walk. Now, S of t is a discrete state, discrete parameter random process, it is a Markov chain. Now, what I am interested here is what happens to this random walk as we take limits of delta x going to 0 and delta t going to 0. If I do that, limit of delta x going to 0, delta t going to 0 of expected value of s, I get t into p minus q delta x by delta t, which is a meaningful limit because both delta x and delta t are going to 0. So, it can be a meaningful limit. But on the other hand, if you look at a similar limit on variance, that is limit delta x going to 0, delta t going to 0, you look at variance, we have to look at 4 p q t delta x square by delta t. As delta x goes to 0, the numerator goes to 0. So, this can be written as delta x into delta x divided by delta t. So, you can see that the variance goes to 0. That means, if a variance is 0, that corresponding quantity is essentially deterministic. So, in the limit of delta x going to 0 and delta t going to 0, S of t becomes a deterministic function. This is not an interesting limit from the point of view of probabilistic analysis, right. S of t is a random walk which is a discrete state, discrete parameter random process, but under this limit of delta x going to 0 and delta t going to 0, we get a deterministic process. So, this is not interesting. What can we do now? Let us do the following. Now, let us consider the limit of simple random walk in which delta x square goes to 0 as delta t goes to 0. In that case, what happens? I will rearrange these terms slightly. I will write delta x as sigma delta t, and p and q I write in this particular form. I introduce parameters mu and sigma, and I can show that under this assumptions, the expected value of S of t goes to mu t and variance goes to sigma square t. Mind you, the limiting operation is quite peculiar. It is delta x square goes to 0 as delta t goes to 0. That means, as delta x goes to 0, square root of delta t goes to 0. So, the resulting process is known as a Wiener process. Okay, a simple random walk in which delta x square goes to 0 as delta t goes to 0 leads to a random process which is continuous in time and state, and that process is known as Wiener process. The process is Gaussian because S of t is obtained by adding independent random variables, and we can invoke central limit theorem and prove that the process is actually Gaussian. The process is non-stationary because mean and variance function are functions of time, and if mean is 0, we say that the process is a Brownian motion process. Okay. Now, without loss of generality, we take B of 0 to be 0. Okay. So, a Brownian motion process is a non-stationary Gaussian random process which is obtained as the limit of a simple random walk in which delta x square goes to 0 as delta t goes to 0. Because of this peculiar property, the sample behavior of Brownian motion will have many pathologies, and that we need to understand if we want to proceed with these models. Now, let us look at this random walk a bit more closely. S of t is sum of I equal to 1 to n xi, therefore, Sn can be written as xn plus Sn minus 1 as shown here. So, Sn is a process with independent increments, Sn is Markov, Since Wiener and Brownian motion processes are obtained as limits of random walk, the Wiener and Brownian motion processes are also Markov in nature. Okay. Now let us look at some of the properties of Brownian motion process. I have derived the mean, and mean is 0 and variance we have derived. Now let us look at mean is 0 and variance is sigma square t, that is what we have done. Now let us look at autocovariance of B of t. Let us consider two time instant t and s so that t is greater than s, and we consider the increments b of t minus b of s and b of s minus b of 0. Okay. So I am considering 0, s and t 3 time instants and looking at the increments. Now since the process has independent increments, the expected value of b of t minus b of s into b of s into b of 0 is 0, because process has independent increments. Now b of 0 I have taken it to be 0, therefore b of s into b of t minus b of s is 0. So that would mean expected value of b of t into b of s is nothing but b square of s, which is sigma square s. So here I am assuming t is greater than s. If you assume s to be greater than t, we get this expectation to be sigma square into t, or in other words I can write autocovariance of b of t as expected value of b of t into b of s is sigma square into minimum of t comma s. Okay. So I will write RBB t comma s as sigma square minimum of t comma s. Now let us consider s to be greater than t. I am interested in derivatives of Brownian motion process. So if I now differentiate the autocovariance with respect to t, I will get, if I assume s to be greater than t, the RBB will be sigma square t with s greater than t. Therefore this derivative can be written as sigma square into unit step function s minus t. If you now differentiate the next time, the step function becomes a Dirac delta function and I get sigma square s minus t. We can also consider situation t greater than s separately, and using similar logic we can also show that dou square r RBB t comma s dou t dou s is sigma square Dirac delta of t minus s. But if you recall, Dirac delta of Ax is nothing but 1 divided by modulus of A into Dirac delta of x. So using that property we can show that the second derivative of RBB with respect to t and s is not, it can be written as sigma square delta of t minus s. This is, as we know, is autocovariance of a white noise process. Okay. So we have RBB of t comma s is sigma square minimum t comma s and its second derivative is sigma square delta of t minus s. Sigma square delta t minus s is the autocovariance function of a white noise process. Therefore, a Gaussian white noise process can be viewed as a formal derivative of a Brownian motion process. Okay. Now you should notice that BMP is not pathwise differentiable in the mean square sense, because as limit t tends to s we are already getting this as Dirac delta function that shows that it is not differentiable in the mean square sense, right. Pathwise it is not differentiable, but if you differentiate the autocovariance of the Brownian motion process and allow Dirac delta representations in that generalized sense, we get the second derivative of Brownian motion, autocovariance of Brownian motion process leads to the autocovariance of a white noise process, right. Therefore we say that white noise, Gaussian white noise can be interpreted as a formal derivative of Brownian motion process. The word formal emphasizes that I am not talking about samples. A sample of a white noise do not exist, because the variance of white noise is infinity and therefore it is not physically realizable. On the other hand, I can write dB by dt formally can be written as the formal derivative of Brownian motion is white noise. I can write the increment of a Brownian motion process as W of t into dt. Okay. So the increments of Brownian motion process delta Bt is B of t plus delta t minus B of t. What is mean of this? Mean is 0. What is its variance? It is B of t plus delta t minus B of t whole square. You expand this and we need autocovariance of B of t plus delta t and B of t, and we know that it is sigma square minimum of t comma s. If you use and simplify this, we can show that the variance of the increment is sigma square delta t. You should notice that increment is on delta t, but variance which is square is again linear function of delta t. Now, let us look at a simple problem. Dx by dt is white noise with initial condition x of 0 is x naught, and mean of this is 0 and autocovariance is a Dirac delta function. Now, this is the Gowning equation. I will write this as dx of t as dbt with x of 0 as 0. Now, we have this Fokker-Planck equation dou p by dou t, which is minus dou by dou x alpha 1 x comma t p of x comma t, etc., etc. What is alpha n? Alpha n are these derivative moments which involves nth moment of the increment. Now, let us start with alpha 1. Alpha 1 will be limit delta t going to 0 1 by delta t dB of t. X of t plus delta t minus x of t is dx of t, which is dB of t. So, dB of t condition x of t equal to x is 0, because expected value of dB of t is 0. Alpha 2 is expected value of dB of t whole square condition x of t equal to x, and this is 2d delta t, and delta t gets cancelled and I have 2d. Now, if you consider alpha 3, it will be dB cube of t, and expected value of dB cube is 0, because B of t is a Gaussian random process with 0 mean. So, expected value of cube of a random Gaussian random variable is 0. You consider fourth moment will be 3 into fourth power of the variance, and this will involve delta t square, and delta t square in the numerator divided by delta t will be delta t, and as delta t goes to 0, alpha 4 goes to 0. So, all higher alphas go to 0 for based on similar logic, and therefore, the kinetic equation terminates at only 2 terms. So, this is a kinetic equation that we have to write. Now, we are talking about derivative or formal derivative of Brownian motion process. Therefore, the boundaries are at x equal to plus minus infinity, because we are talking about Gaussian random processes. So, the initial condition will be this and the boundary conditions would be this. So, we have to solve this equation under these prescribed initial conditions and boundary conditions. Now, in this particular example, it is easy to solve this. We can consider the characteristic function. I will call it as m of theta comma t, which is the Fourier transform of the density function, and I will express now the density function in terms of the characteristic function, and find out now dou p by dou t and dou square dou p by dou x square. This is like using Fourier transform technique to solve partial differential equation. So, dou p by dou t would be in terms of this, and dou square p by dou x square will be in terms of this. Now, you substitute these two into the original equation, I get this, and a little bit of simplification would lead to an ordinary differential equation for the characteristic equation, the characteristic function, and I can get m of theta comma t is m naught exponential minus d theta square t. Now, what is m theta comma 0, which is actually the Fourier transform of the density function, probability density function at t equal to 0, which is Dirac delta function, and I get this I theta x naught. So, this m naught, which is arbitrary constant, now turns out to be this. So, if I now substitute into this m naught I have already written, this I theta x naught minus d theta square t. This is nothing but the characteristic function of a Gaussian random variable. So, it would mean that probability density of x comma t is a normal function with mean x naught and variance dt, and this is written here. So, from this you can see that x of t is non-stationary, Gaussian and Markov. So, I am talking about a formal derivative of Brownian, actually this we are talking about Brownian motion process. Okay, dB by dt equal to w of t is the equation I am solving. So, these are properties of B of t. This is a Brownian motion process that I am talking about. So, this tells us, briefly illustrates how the kinetic equation can be used to analyze a relatively simple problem. we would be interested in this approach if this approach can be generalized to more complicated systems. So, how do we do that? Before we get into that, there is an alternative derivation of the Fokker-Planck equation in terms of the Chapman-Kolmogorov equation, and that is instructive. So, let us go through that. So, let x of t be a scalar Markov random process, and by virtue of the Chapman-Kolmogorov Smolchowski equation, the following would be true. This integral equation is true, where T1 is T1 tau T2 are ordered as shown here. Now, this is an integral equation. Okay. Now, for a given integral equation, we can always derive an associated partial differential equation, and indeed that partial differential equation would be the Fokker-Planck equation. We can show that. That would mean Fokker-Planck equation represents the consistency condition for the process to be Markov, just as this CKS equation represents the consistency condition for process to be Markov. So, how do we do that? We start by considering an integral minus infinity to plus infinity r of y dou p by dou t dy. This r of y is presently an arbitrary function that admits Taylor's expansion, that means it is smooth and well behaved, and also it approaches plus minus infinity sufficiently fast. What exactly is meant by this will become clear as we go along. It is a well behaved function. Now, let us look at this integral I, and I will write this as this derivative in terms of this limit dou p by dou t is nothing but 1 by delta t p of t plus delta t minus p of t divided by delta t as delta t goes to 0. So, I will look at this now p of I t plus delta t condition x naught t naught, and I will use the CKS equation to represent that in the first term. This is this, and the second term remains as it is. So, I have utilized the fact that x of t is Markov. This r of y I will now expand in Taylor's expansion around x. I will consider r of y and I expand around x as shown here, and this expansion is permissible because I have assumed r of x is sufficiently smooth. So, I go back and substitute this into the first integral. So, r of y into the terms involving in the CKS equation I will write like this, and r of y I am writing in terms of Taylor's expansion, and this remains as it is, and I am now considering the first term here r of x into this here, and we can interchange order of integration, and one of the integration with respect to y the term is actually 1 because it is the area under probability density function, and I get r of x p of x at t condition x naught t naught, and there is a term, and this term gets cancelled with the second term that is present here. So, this term we can now forget. So, what we are left with now are terms contributing from the second term onwards. If you do that, first term is gone. So, I am writing this in terms of this, and a little bit of manipulations of rearranging these terms will show us that this I can be written as r prime of x into a, r double prime of x into a, this is b, r triple prime into c, etc. into dx. Now, this is what it is, where these a, b, c, etc. are the nothing but the incremental moments, the delta x that I was writing, that alpha n I was writing in terms of moments of delta x, the same things here. Now, if you consider the first term in this r prime of x a x comma t p x colon t dx, I can do an integration by parts, okay, and the first term in the bracket goes to 0 because I am assuming that r of x goes to 0 faster than the other terms. That is what I meant when I said r of x goes to 0 as x goes to infinity sufficiently fast. That is, it should be faster than this, so that this term is 0. I restrict my r of x to only that. So, I get this expression, that is this expression. Now, the second term which involves double derivative will again integrate by parts twice, and here again I put this as 0 with an assumption that r prime of x goes to 0 as x goes to plus minus infinity. That is what again I meant what is meant by sufficiently fast. So, I get here these terms as r of x dou square by dou x square into this. Now, let us go back to the definition of I and write in these terms of this and use these simplified versions. I get an equation r of x into a set of terms inside the bracket into dx equal to 0. Since r of x is arbitrary, it follows that the term inside the bracket should be 0, because this is true for all r of x, and we get that this is nothing but the Fokker-Planck equation that we derived by an alternate argument. Here again there are infinite number of terms shown here, but if you are dealing with systems driven by Gaussian white noise, where Gaussian white noise is obtained as formal derivative of Brownian motion process, we have seen that all these higher order terms go to 0 and we are left with only 3 terms in this, and that becomes amenable for possible solutions. Okay. Now, let us make few remarks. This equation displayed here is also known as Kolmogorov forward equation. The word forward here is because it contains the derivative dou by dou t of the density function, which refers to time derivative with respect to t which is greater than t naught. So, that is why we call it as forward equation. So, this connotation also automatically implies that there is something known as backward equation. So, that we will come to later, and we will show that backward equations are useful for solving first passage times and problems of first passage probability and so on and so forth. Right now, the forward equation. The parameter a, b, c are known as derivative moments, which are nothing but the alphas that I discussed in kinetic equation. They are exactly the same. So, they are actually moments of the alpha. A is actually the first order moment, b is the second order moment of the increment, c is the third order moment of the increment, and so on and so forth. Now, we have already discussed properties of Brownian motion process, and we will now restrict our attention to models of systems driven by white noise excitations, and this leads to what are known as Ito's stochastic differential equations. So, here we restrict our attention to excitations which are formal derivatives of Brownian motion process, and in deriving now the incremental moments we will use properties of increments of Brownian motion process. Now, consider the differential equation governing the n cross 1 vector x of t, dx by dt is some function of t comma x of t comma f of t, where t is greater than t naught and x of t naught is specified. Let f of t be a m cross 1 vector random process, and capital F is a n cross 1 nonlinear function. If f of t and capital F are such that this integral t naught to t, suppose I integrate both sides with respect to t, I will be left with t naught to t f of tau x of tau f of tau d tau. If this integral exists in a mean square sense, then the solution can be written as x of t minus x of t naught to t f of tau comma x of tau f of tau d tau, etc. This is a solution, provided these integrals can be interpreted in a mean square sense. If on the other, if f of t, if elements of f of t are Gaussian white noises, then this kind of this integral does not exist in the mean square sense, and the equation A loses its meaning as a solution, because the integral itself is not defined in the mean square sense. So, for sake of illustration, let us consider the scalar equation dx by dt is f of t comma x of t plus g of t x of t into w of t, where w of t is a 0 mean Gaussian white noise. Now, we recall that w of t is a formal derivative of Brownian motion process, that means dw of t can be written as db of t. Now, I can rewrite this equation as dx of t f of t comma xt dt plus g of t comma x of t into dbt, where t greater than or equal to 0 and x of 0 is specified. Okay, in terms of increments I am writing. Now, I can therefore now write this as x of t minus x of 0 as 0 to t f of tau comma x of tau d tau plus 0 to t g of tau comma x of tau dB of tau d tau. Let us look at these two integrals. First of this integral you know is integration with respect to tau. So, this integral can be interpreted in the traditional Riemann sense in terms of area under the curve and so on and so forth. Whereas the second integral, if you look at, this is random, this is also random. This integral does not exist in a sample sense, but can be defined in a mean square sense. Okay. So, this that means you can't have a Riemannian interpretation for this, but it can be interpreted in a mean square sense, and that is what Ito's stochastic integral theory enables us. So, this equation B, we call it as Ito's stochastic differential equation. It is a differential equation to the extent that this is an integral equation where this integral is interpreted suitably in a mean square sense. So, there are two references that you may find useful to study this further. In these lectures I will not be getting into greater details of Ito's SDEs, but these two references, one by Zarzwinski, stochastic processes and filtering theory, and other one is by Soong, random differential equations in science and engineering, which has descriptions which perhaps are accessible to engineers. Now, let us look at this equation again. Dx of t is f of t comma x of t dt plus g of t comma x of t dbt. We know that b of t has independent increments, and from this it follows that x of t is Markov. How do we explain that? The claim I am making is solutions of Ito's differential equations, stochastic differential equations, have a Markovian property. Therefore, I can write the associated Fokker-Planck equation and solve them. That is the line of thinking that I am trying to develop. Now, how do we show that the solution here is Markov? So, let us consider time instant t, t plus delta t and t plus 2 delta t. The change from x of t to x of t plus delta t is due to change in b of t from p of t plus delta t minus b of t. This is a change in the Brownian motion process. So, this produces this change. Similarly, change from t plus delta to t plus 2 delta t, t plus delta t to t plus 2 delta t is due to this increment b of t plus 2 delta t minus p of t plus delta t. These increments are independent. That means, the increment b of t plus delta t minus b of t and b of t plus 2 delta t minus b of t plus delta t are independent. Consequently, the incremental changes in x of t, which is this and this from t to t plus delta t and t plus delta t to t plus 2 delta t are also independent. That would mean x of t has independent increments and therefore, it has Markovian property. The question therefore, now that we would be interested further would be, can we derive the Gowning FPK equation and solve it? How do we proceed? So, let us consider a simple example, x naught plus beta of x equal to w of t, where t is greater than or equal to 0 and x of 0 is x naught. W of t is a Gaussian white noise, 0 mean and autocovariance given in terms of Dirac's delta function. So, I can rewrite this equation in terms of Ito's SDE as dx is equal to minus beta of x of t into dt plus dbt. What is the quantity of interest? Probability density function of x colon t conditioned on x naught at t equal to 0. So, therefore, the initial condition would be p of x semicolon 0, x naught semicolon 0 is Dirac delta function of x minus x naught. Boundary conditions, as x goes to plus minus infinity, this probability density function goes to 0. These are the incremental moments that I would be needing to formulate the Fokker-Planck equation alpha 1 and alpha 2. So, how do we derive them? Alpha 1 is limit of delta t going to 0 1 by delta t, the first order moment of the increment x of t plus delta t minus x of t conditioned on x of t equal to x. So, what is dx of t? Dx of t is minus beta of x of t dt plus dbt. So, minus beta x of t dt plus dbt. What is the expected value of this conditioned on x of t equal to x? It is nothing but beta of x. expected value of dB of t is 0. What is the second incremental moment? The square of this increment condition x of t equal to x. Square of this is minus beta dt plus dBt whole square. So, you expand this, it is beta square delta t square dB square minus 2 beta into dB of t. Now, this term it will be beta square into delta t square divided by delta t would be delta t, as limit delta t goes to 0, that goes to 0. The second term will be 2d and this mean of dBt is 0, therefore, this term goes to 0. So, I am left with 2d. So, therefore, what is the Fokker-Planck equation? The dou p by dou t is equal to dou by dou x of beta of x into p plus d into dou square p by dou x square, where p is this transition probability density function. Okay. So, from the Gowning equation of motion, I have been able to derive now the FPK equation, which can again be viewed as equation of motion for evolution of probability density function. Now, how do we solve this? Okay. A standard method for solving partial differential equation is using method of variable separation. So, we can seek the solution in the form psi of x into t of t. So, you substitute that into this, it becomes psi of x t dot plus beta of x psi of x prime into t of t plus d psi double prime into t. You divide by psi t and simplify, I get t dot by t is equal to beta psi prime divided by psi plus d psi double prime by psi, and if you look at this term, it is a function of time alone, this term is a function of x alone. If you change time, this second term cannot change. If you change x, the first term cannot change. So, only way they can be equal is they have to be equal to a constant. So, I get t dot minus lambda t equal to 0 and I get another equation for psi, the second order equation with boundaries at plus minus infinity. So, this is the equation, this is an eigenvalue problem. Lambda is eigenvalue, psi of x will be the eigenfunctions, and depending upon the nature of beta of x, the solution can be obtained in the form I equal to 1 to infinity ai exponential lambda I t psi I of x. The constant ai's can be obtained using the initial conditions, that at t equal to 0 this function should go to a Dirac delta function and we will get ai. Now, the task of finding psi of x depends on choice of beta. Okay. So, they are typically obtained in terms of hypergeometric functions like Hermite polynomials, Lagrange polynomials and so on and so forth. So, at some point during the next few lectures I will touch upon some of these illustrations. Right now I will proceed with how to formulate the Gowning equation. I am not so much focusing on the exact methods for solution. Now, before we leave this, we have to see here, if we focus on this equation, if as t tends to infinity, if system admits a steady state, then the probability density function will become independent of time and I get dou p by dou t equal to 0. So, if that happens, the Gowning equation for stationary solution will be an ordinary equation, ordinary differential equation d by dx of beta of x into p plus d into d square p by dx square equal to 0. This can again be solved. Okay. This is easy to solve. Okay. I will illustrate the solution later when I consider specific examples. Now, we will come to one of the simplest problem in vibration analysis, namely a single degree freedom system under Gaussian white noise. So, let the system initial condition be x naught and x naught dot, and mean of Wt is 0 and autocovariance of Wt is 2d into Dirac delta of tau. This is a second order differential equation. First what I will do is I will introduce the state vector x of t, x1 consisting of x1 and x2, where x1 is x and x2 is x dot. This is displacement and this is velocity. So, what will be the x1 dot is actually x dot, therefore, dx1 is x2 into dt, that will be the first equation. dx2 by dt would be x double dot, which is equal to 2 eta omega x dot omega square x taken on the other side plus w of t. So, that would be dx2 would be therefore minus 2 eta omega x2 minus omega square x1 into dt plus dB of t, because w of t dB of t is what? dt into w of t, because Brownian motion we are interpreting as white noise, Gaussian white noise we are interpreting as formal derivative of Brownian motion. So, I get this equation. So, now I am ready to launch my calculation for finding alpha 1 and alpha 2. So, the probability density function that I am looking for is now actually for the vector x1 x of t, it is not scalar now, okay, because this vector has 2 elements. The Markov property is satisfied by x of t, it is not satisfied by x1, it is not satisfied by x2, it is satisfied by x of t. That is what the initial remark I made, that elements of a vector Markov process need not be Markov themselves. And also you can see the displacement and velocity will have different levels of differentiability, because x double dot is proportional to a white noise. So, so therefore, x dot is not differentiable, but x is differentiable in the mean square sense. Okay. So, that is another point that I made earlier. Now, the evolution equation for the probability density function, the TPDF, is shown here, and now to proceed further I have to find now these alphas here and alphas here. How do we do that? Alpha j is limit of delta t going to 0, 1 by delta t, the increment condition x of t equal to x tilde, and alpha ij is actually xi of t plus delta t minus xi of t into xj of t plus delta t minus xj of t, condition x of t is x tilde. Now, alpha 1 let us look at, limit delta t goes to 0, 1 by delta t, dx1 is x2 dt, therefore, x2 dt condition x1 is equal to x1 of t equal to x1, x2 of t equal to x2, this is nothing but x2, because this is x2 here, it is conditioned at x2. Alpha 2 would be minus 2 eta omega x2 minus omega square x1 plus dB of t, condition on x1 of t is x1, x2 of t is x2. So, this will be minus 2 eta omega x2 minus omega squared x1, the third term is 0 because expected value of dB of t is 0. Alpha 1 1 will be what? Square of x2 square into dt square, condition on x1 t equal to x1, x2 t equal to x2. Now, under this limiting operation this will be 0, therefore, alpha 1 1 will be 0. This will be x2 square dt square, 1 by delta t, as delta t goes to 0, that will be 0. So, I get alpha 1 2 equal to alpha 2 1 equal to 0, and alpha 2 2 you have to square this and take expectations by conditioning this way, and the first two terms will vanish and the cross term will vanish, and dB square of t will lead to 2d. Okay, that we have done previously, therefore, I am not repeating here. So, I am ready with now the governing equation, this is the general form, and we have derived now these alphas, and if I substitute into this I get dou p by dou t as minus x2, dou p by dou x1, dou by dou x2 into alpha 2 p plus d into dou square p by dou x2 square. The initial conditions at t equal to 0, displacement is x naught, velocity is x naught dot, and both are Dirac delta functions. So, as t tends to 0, this condition would be satisfied, and similarly I have at boundaries plus minus infinity the density function is 0. So, x1 equal to plus minus infinity, this is 0, x2 equal to plus minus infinity equal to 0. So, the problem now is on hand now reduces to the solution of a partial differential equation under these initial and boundary conditions. Okay. So, this is a different exercise in mathematics that can be done. Okay. We will see how it can be done in the next lectures, but right now we are focusing on how to formulate the problem. So, again let me emphasize that the FPK equation can be viewed as the equation of motion governing the evolution of this probability density function. Okay. Now, if a steady state is possible, as t tends to infinity, the probability density function would become independent of time, therefore, dou p by dou t would go to 0, and I get a simplified version of this equation, which is still a partial differential equation, because now I have two independent variables x1 and x2, and if you are interested only in stationary solutions, we can directly tackle this equation. You should of course independently verify whether the mechanics of the problem admits the steady state solution. If this, for example, if system is undamped, there will not be any steady state, although you can write such equation and try to see what you get, it will not be correct. Okay. And these boundary conditions, of course, again at plus minus infinity on x1 and x2, the density functions are 0. So, these are the associated boundary conditions under which we have to solve this reduced partial differential equation. We consider stationary inputs. So, I want to now go in some sequence. I will consider non-stationary excitations, non-linear systems, non-Gaussian excitations and multi-degree systems, and I will show that for each of these cases we can formulate the Gowning-Fokker-Planck equation. Okay. So, let us consider now non-stationary inputs. So, the same single degree freedom system, now it is driven by E of t into W of t, where E of t is a deterministic modulating function. W of t is as before a white noise with 0 mean and autocovariance in terms of Dirac delta function. As before, I define the vector x of t as x1 x2 and get this equation in state space representation, and again look at the Gowning-Fokker-Planck equation. Here nothing really changes, we get same values for alpha 1 and alpha 2, except that for alpha 2 2 I get the effect of the envelope, which is 2d e square of t. So, the Gowning equation will be quite identical to what we got earlier, except that now I have in this term d into e square of t dou square p by dou x2 square. Clearly in this case we cannot talk about a steady state solution because on the right hand side there is t. That means if the incremental moments themselves are functions of time, then there is no basis on which we can talk about steady state solutions. P will continue to be a function of time even for large times. Okay. How about non-linearity? So, I introduce a slight change, I add a cubic nonlinear term. So, the system now becomes a Duffing's oscillator with cubic nonlinear term. The problem formulation is essentially similar, except that one of the incremental moments would now change to allow for this additional influence of nonlinear term. So, I have dx1 as x2 dt, dx2 as 2 eta omega x2 omega square x1, this is the new term minus alpha x1 cube this. Now, alpha 1 would remain as x2, but this alpha 2 would now contain the influence of nonlinear term, and alpha 1 1, alpha 1 2 and alpha 2 1 will be 0, alpha 2 2 will be 2d. Now, the Gowning equation will have the influence of nonlinearity through an additional term in the coefficient here. Okay. So, here again, since the incremental moments are independent of time, one can think of steady state solutions and we can look at the reduced partial differential equation governing the steady state solution. So, I will show in the subsequent lectures that an exact solution to this problem is obtainable. That means, for a Duffing oscillator under white noise, the steady state response is exactly determinable. It should be appreciated because if you consider a Duffing oscillator under harmonic excitation, under steady state no exact solution exists for the deterministic problem. But when excitation is white noise, the problem somehow becomes simple enough to allow for an exact solution. Now, we can make the problem slightly more complicated. We can have external excitation and also parametric excitation. So, I have now a linear single degree freedom system with 3 white noise excitations, 2 of them are parametric and one is external. So, again I consider system starting from x naught and x naught dot, and the 3 random white noise processes I will assume that they are all correlated, and this is the matrix of cross covariance functions. So, dBit dBj t plus delta tau is 2dij Dirac delta of tau. Okay. Now, again I define the state vector as x1 x2 which is x dot and get the equations in this form. Now, there will be additional terms here containing the increments of 3 Brownian motion processes, and they are multiplied by system states for the 2 terms, and of course, the third term is an excitation. Again we are interested in finding the evolution of the transition probability density function, which is now function of x1 x2 t conditioned on x naught and x naught dot. So, that FPK equation will have this form, and we need to now determine alpha j and alpha jk. Okay. This is dx1 is x2 dt and dx2 is having these additional terms. Alpha 1 would be still x2, alpha 2 would not change because the expected value of dB of t and other these terms are still 0, therefore, this would not change. So, here we have to add dB1t minus alpha x1 dB2t and their mean values are all 0, therefore, it would still be this. Alpha 1 would again be 0, similarly alpha 1 2 and alpha 2 1 will be 0, but alpha 2 2 will now be expected value of square of this conditioned on the initial x1 of t is x1, x2 of t is x2. So, this involves some calculations. The only term that will remain after we take expectation and apply these limits will be associated with variances of these 3 terms and they and the cross covariances, and if we do that I get this alpha 2 2 to be this. Okay. Now, I have governing FPK equation would be dou p by dou t minus x2 by dou p by dou x1. This term also would not change, but now the terms involving second derivative will be more complicated. They will have these terms. The initial conditions would remain the same, the boundary condition would also be the same, and if a stationary solution exists, okay, we are not sure when there are parametric excitations, we are never sure if there is a steady state. Okay, system if it becomes unstable, there may not be a steady state. Okay. So, if a steady state exists, it is governed by this reduced equation. Again, a general class of say deterministic problems with this kind of parametric excitation terms is not solvable. There are no exact solutions in deterministic case, but it turns out that for certain cases of problems with parametric excitation, we can get an exact solution using Fokker-Planck equation. Furthermore, I am now right now talking only about probability density function, evolution of probability density function. From that evolution of probability density function, I can also derive the evolution equations for moments, response moments. It turns out that for this class of problems, linear systems with parametric Gaussian white noise excitations, the moment equations are exactly solvable. So, the Fokker-Planck equation approach is a source of exact solutions for a wide class of problems where the counterparts in deterministic analysis are not solvable. Some more examples. Suppose I have been talking only about white noise excitations. Suppose there is a filtered white noise excitation. The excitation is not white, but it is colored. So, f of t I model it as output of a single degree freedom system which receives a white noise excitation. Now, to handle this problem, I define an extended vector of response quantities x dot and f dot. That means f of t is the excitation, but excitation itself is modeled using a linear system driven by white noise. So, we can show that this extended vector will have Markov property, right, and therefore, I can write the governing FPK equation for that. So, I have dx1, dx2, dx3, dx4 and I can go through this, find out alpha 1, alpha 2, alpha 3, alpha 4 and get the governing Fokker-Planck equation even for this case. So, I can write these equations and write down the boundary conditions. Now, there are 4 independent spatial variables x1, x2, x3, x4 in addition to time. Okay. So, but in principle the problem is formulated. Now, how about linear multi-degree freedom systems? Okay. I have been talking about single degree freedom system. So, I can multiply this governing equation by M inverse and write it as x double dot M inverse C x dot, M inverse K x and M inverse this. So, I can introduce now a 2n dimensional state space y I and y double I and write an equation for y I and y double I and cast it in the form of the Ito's differential equation. Okay. So, it is possible to cast this equation in the Ito's form, and the moment we put in the Ito's form I can derive, I know the solution is Markov and I can derive the governing Fokker-Planck equation. Okay. So, now what happens if nonlinear system is multi-degree and nonlinear, say f of x comma x dot. Here again I can introduce the extended vector of yi y double I and I can still write the Fokker-Planck equation where this M inverse f of y is my p of y. So, this f which is a nonlinear function here is still represented in my equation. So, now if we consider a general n dimensional Ito's stochastic differential equation, I have shown that a multi-degree freedom system can always be cast in that form. So, we can consider a general Ito's multi-degree equation where there are nonlinear drift and diffusion terms. This is not a drift term, this is not a diffusion term. I can use this state space representation and derive the incremental moments in terms of these f and these g's, and I can still get the associated Fokker-Planck equation. So, the formulation of the Fokker-Planck equation itself is fairly general. It can handle parametric excitation, it can handle nonlinear systems and so on and so forth. So, in the next lecture what we will do is we will think of how to solve the governing Fokker-Planck equations and how to get transient solutions, how to get steady state solutions, and when do we get exact solutions for these problems, and what approximate strategies that we can develop, and how to derive moment equations from the governing equation for evolution of probability density function. This we will consider in the next lecture. We will conclude this lecture at this stage.